Very good. Thank you very much. So good afternoon and hello to all. We'll start with a quick introduction. As Clayton's already done, but Chase. So my name's Tom Piper. I've been in the manufacturing industry since the mid 90s. I have over 15 years of machining and programming, both 3 and 5 axis, 10 years in management, part-time teacher at the local college, and 13 years of consulting in the Windsor, Ontario region. This has all led me to Next Gen Solutions and as a strategic account executive and technical advisor. So the majority of my experience is in the mold sector, and a lot of the topics here will reflect that. But generally, these applications can apply to manufacturing as a whole. So today we're going to discuss many components associated with success of CAD/CAM design and manufacturing, one-off or what you may call unique components. So a lot of companies are doing production, but today we're going to focus a little bit more on one-off components. As the demand for manufacturing throughput and precision increases, and the workforce and skill sets seemingly decrease, we need to channel our resources into smoother, efficient, and more departmentally organized way of manufacturing. Often we purchase software with the intent of filling the demand of a specific manufacturing operation. We think once we purchase the right software, sign up for training and support, and all my problems are solved, and we can place an X next to the manufacturing checklist. In reality, machining aspects of manufacturing is arguably the most challenging and technical component of the process. If we don't support the process in many more ways than simply adding software, machinery, and personnel, we're placing a tremendous amount of pressure on the programmers and machinists alike. So in terms of capital expense, your machines are arguably the largest cost associated with manufacturing process. So it would only make sense to invest wisely and to focus heavily on ensuring that this part of the process is as efficient and seamless as possible. This is also true when considering future investment in more machinery. If an acquisition of more machinery is made to accommodate a higher volume of work, while the measurables of the machine utilization are not above 80%, spindle runtime, lights out, unmanned or unattended machining, you may be adding to the inefficiencies of your operation. So how do we solve some of these challenges? First, we will discuss some of the solutions surrounding PowerMill, and after we will have a brief look at some of the options in PowerMill that will help with these challenges. Standardization of workflow and processes. Okay, we're talking about PowerMill here specifically. Aside from the obvious, there's all different levels of users of the software. So we're just going to start with, this is relatively basic introduction to some of the automation of PowerMill. So PowerMill standardization templates, standardized templates rather. So for roughing, semi-finishing, stock model, boundary creation, finish machining, ultimately the goal is to have all programming done by each individual to the same standard. So consistent process, feeds, speeds, depth of cuts, radial depth of cuts, so this in turn is going to drive down your tooling cost. It's difficult to measure tooling costs when machining one-off components without programming standards. But when all programming is done to a standard, this becomes very predictable over time. So custom macro creation specific to company and machining requirements. So no two shops run the same. PowerMill is the most user customizable software on the market, allowing users to standardize according to their unique requirements. So modifying the way we design. Reverse engineering, if you have the luxury of manufacturing or designing your own components, rather, then you may have the luxury as well to design almost in a reverse engineering manner according to the machine and the tooling capability. So in other words, you've got a certain selection of tools on the shop floor. Your designers should be educated and know that when they're designing their components, that they design things with a larger corner radius for chatter-free cutting, not only to make the corner radius the size of the existing tooling base database, but larger to avoid chatter and increase tool life. Color coding for surface default. Coloring key components, a specific RGB, red, green, blue, and creating macros to add or remove extra material. This is the same for safety and collision avoidance. So adding safety thickness to machine components, such as the table or any other obstacles for 5-axis specifically, would drastically reduce the chance of collision. So surface defaults basically is you're just adding artificial thickness or adding artificial material within PowerMill. So the spindle and the tool, not so much a spindle, if your spindle is drawn up as part of your tool, I should say, and automatic collision avoidance is on during program calculation, then it's very difficult, not impossible, but very difficult to crash your machinery. Okay. Known process before machining begins for each component. Having personnel with a machining background preparing all data prior to release, including file translation to native PowerMill format. So this would avoid, having a translation issue on the floor. One small surface in a large job rather can cause a lot of problems in terms of calculation speed. So filtering that through an individual before those files get to the floor, I think is very important for sure. So going one step forward and 2 steps back is not only counterproductive, but interrupts the workflow of other departments and could lead to costly mistakes. So work holding. Again, these are all topics that revolve around PowerMill, not so much PowerMill specifically, but in conjunction, and I'll show you that in just a few moments on PowerMill, little demo. So work holding. Knowing where the 0-point work holding, I should specify, knowing where the workpiece will be in the machine in advance. So the ability to program in advance in PowerMill. So you can program today, you can run it tomorrow or next week, which really helps the scheduling in production, gives you an advantage that way as well. So it also will increase accuracy, precision, and throughput. Okay, so programming consistency with all employees. So I like to tell a story, like if you've got a job, say 5 jobs, they're all identical, and they're programmed by 5 different programmers. And once they're machined, you put them on the floor, they should all look like they were programmed by the same programmer. Now, this is a high level. To me, it's a very high level of success when you can take a group of people and have a very similar end result in terms of machining. Okay, once your team embraces this modified way of working, work pieces will become very consistent in terms of accuracy and cycle time. So quality control and measurables, creating tolerances that are specific for each component. So plus or minus tolerance separate for each component relative to its function is what I'm saying. So every component, and again, we're talking more mold and die, maybe more mold and die, but every different area on a mold serves a different function. So the tolerances are different. But the point is you want to measure those. So over time, you're going to see implementation of standards and increase the quality. So Eventually, this will lower rework and programming errors too. So another facet here is setting up your network for success. Ensuring the programmers and machinists are using the most up-to-date revisions for all CAD models. So we also sell a software vault. This would be a solution you might want to look into if you're interested in decreasing any errors associated with data. So ensuring the programmers and machinists are using most up-to-date revisions for all CAD models. Macros, templates, tool databases, standards to be stored on one common location on the server. Again, this is very important because once you standardize things, collectively as a team, you can make changes, but you want all of your macros and all of your templates and all your tool databases to be located on a server for access to anybody on the floor. Which would allow, any programmer on your shop floor to program from any machine at any time. Again, yeah, so file and folder naming structure also. So measurables, we're going to get into measurables here. So tooling costs. Your baseline is measured by today's monthly spending. Okay, that's where you start. If you're not measuring that, you might want to determine what that number is now. So as you implement changes, you can measure and see that it's working. You're seeing success. As the volume of work increases and process and standards are in place, the tooling cost per month to work volume ratio will be greatly reduced in cost. So, if you're producing 10 million in revenue today and your tooling cost is 25,000 a month, in 2 years or a year after implementation of all these standards, you could be at 30 million in sales and your tooling cost may still very well be 20 to 25,000 a month. I have a case study for that example. So let's see. So CMM report, quality and accuracy. Over time, your analytics will see consistencies or inconsistencies that will drive corrective action. Discuss monthly reports for each component group. So reduction in time assembly, also the better the quality of the part, the less time spent assembling. So throughput in production. So standardization of all processes required to machine components will increase work volume due to less rework or reinventing the wheel on every project. So again, it's standardizing everything. You're going to know exactly how you're going to tackle every component before it's on the floor, before it comes to the guys on the machines. And also through the standardization, excuse me, machine lifespan. So you're going to have a reduction in errors, tool breakage, and stress on the machine while cutting. So there's definitely a cost reduction there on your machine and your equipment. Machine runtime. So lights out machining with one-off components to maximize your investment. So monitoring to qualify expansion or capital equipment purchases as well. So this will help you determine if additional staff is required. So essentially, you got a machine that's taking up floor space. You want to make sure that that machine is utilizing its spindle uptime above 80% before you would ever consider purchasing more equipment. And without improving, if you're at 40 or 50%, you'd certainly want to get that machine to 80% or more before spending more capital on more equipment. So scheduling and workflow. Okay. Accurately predicting the cycle time of one-off components will become far more accurate. Okay, maximizing the spindle uptime, prioritizing workflow schedule. So to maximize lights out machining, once you have a better prediction of what jobs, how long they're going to take, and where to schedule those things for a lights out machine. So in other words, you standardized everything. You could program it today, you can run it tomorrow or next week, but you have that luxury because it's programmed and ready to go in the machine. That's all a direct result of the standardizing. So, so now the one thing too, a little bit off topic, but the work culture. I mean, as an employee, you want to come into work and have a tangible return at the end of the day. So it lowers the stress level, which also lowers the human error. Positive, tangible return during shift creates creates a positive work environment, lower employee turnover, uh, the talent pool, recruitment of talent and skilled workers. It's harder and harder to find experienced people. With standardizing everything, outside of PowerMill with your 0 point work holding, you're standardizing your designing, you're standardizing your processes. The time it takes to train and to get somebody up to speed is greatly reduced. So there's a cost savings there as well. So now I'm going to share my screen. I've got a couple of examples here. So just to touch a little bit on the macro side. So there's many ways you can set this up in PowerMill. I'm just going to show you some of the ways that I've done it in the past. If we go to a machine specific, pardon me, I'm going to go here. I'm going to just close this off for a second. And so this particular macro here, what it's going to do, and this would be the same for all your equipment. This is just an example of one. This is going to set up a DMG machine, 5-axis DMG machine. It's going to set your post processor. It's going to load up the machine, the MTD file for collision checking. It's going to load up the machine table, the tool databases, all the templates, everything that machine specifically needs to run and operate with a click. Again, a lot of different users. This is probably a known thing, but just to kind of give you an example here. So this is just going to set all the tolerances within PowerMill. I think a lot of times when people are concerned about calculation speed, they're just leaving it at a very high tolerance. It may not need to be such a high accurate tolerance within PowerMill itself. So a lot of these things here are directly related to the accuracy. So we're opening things up where we need, where we can, and still achieving the accurate machinable part, machine part rather. And then of course, we're loading up all of those components that I specified earlier. And I'm just going to go ahead and run that for you guys. So you're seeing it load surface defaults, as I'd mentioned earlier. And when you see those colors flashing, essentially it's taking the surface defaults and adding 1/8 of an inch of safety surface to the table. So during program calculation, your spindle is going to automatically avoid, if you're turned in on 90 degrees, it's going to automatically avoid the table, greatly reducing the chance of any collisions. So there's that. Now I'm going to show you another model I've got set up here. And just as another example, let's just say we want to get down in this little tab here. And we got a 5-axis machine, so obviously we're going to tip to get away from that wall. So we're going to find a nice sweet spot here like that. And we're just going to say, we're going to run this macro here. It's a very simple macro, but again, it does a few functions all in one. And we're just going to say work plane of view. And we're going to open up our standard templates here. So again, naming structure, file convention, all these things are very important. Everyone on every machine is going to have specific folders and templates specific to their machine. Every machine cuts different. You know, you got 3-axis, you got 5-axis, you got boxways, you got linear guideways. So every program in here is specific to that machine. In this case, we're going to pull up a Z-level finish program. And again, there's no reason that you should be filling out every blank every time you're pulling up a program. These should be set as a default. Every user should be using the same feed speeds, step over, step downs. Once that happens, you know, and it's set like I said per machine, but you're going to see your tooling life is going to go up because you don't have different operators doing things different ways. You know, sometimes the RPMs and the step downs can obviously drastically reduce tool life. So once you collectively decide what those feed speed step downs should be, put them in here, save them off. Everybody's doing it the same way. So we've got this open. We've got our work plane made. Now we're going to go up to a boundary creation. Now, again, there's a lot of reasons this might seem simple, but rest boundary creation, for example, let's say we want to make a rest boundary for a 3-mil ball. I'm just going to show you this here. What's really, really important here is the standards. Okay, so we've got these standards in here. Okay, the tolerance is set. You know, detecting the thickness of the stock, extending the boundary, all these things, when they're not done the same way every time, you're going to get a different result, obviously. So I'm going to run that. So sorry, before I do that, jumping ahead of myself here. We're just going to go ahead and select only the surfaces that we're interested in machining here. And everything else we're not interested in right now. So once you've selected those surfaces, you can simply run this. That's going to set the block form. That's going to create a rest boundary, a reference boundary, a limiting boundary, I should say. And there we have, we will have our boundary just like that. Now, again, instead of going into the boundary creator and filling in all of these blanks, this is now a standard. It's done. Everybody does it the same. The speed in which you can do it, the consistency, it's all going to show at the end result, and the quality. So, and again, you're just hitting a few buttons instead of filling everything in. There's just a couple of examples. Obviously, there's a lot more things that you can do. I just wanted to briefly give you a quick rundown of scratching the surface of the possibilities here. So again, we can go to machine specific. As I'd mentioned, all the machines in this particular example are here. They've all got the same things. You know, so even if you open an old session that was done on another machine, you can simply run these macros here. It's going to set your tool database, your post output, your template database. So in a very short amount of time, you will be ready to take that job, maybe after stress relief or after welding or after different applications, and the job has to come back for rework or more work. You can quickly get moving again. So that that pretty much wraps it up for me. Sorry, oops. Chase.
Yeah, awesome. I'm glad we were able to get a demo in there as well. It's always cool to see like kind of
Brief,
just yeah,
brief.
it's yeah.
The next time we'll dive a little more into some examples, and I really just wanted to explain to everybody or showcase that, it's not just about the power mill.
Hmm.
It has to be about the full operation and other things that complement power mill and the guy running power mill.